In this section, we will study about the G transform. To understand the G transform, we would like to review Fourier transform and the Laplace transform. This is definition for the Fourier transform. Okay, and Laplace transform is given like that. When we replace S, that complex number, with real term is sigma and plus j omega, then we can express Laplace transform in this way. This means that the Laplace transform is a Fourier transform of these terms. Okay. Then in the Laplace transform, it's a S domain. Okay. If sigma equals 0, then this one is just the j omega axis. So the imaginary axis. This axis corresponding to Fourier transform. Okay. In the S domain, real term, that means that real term is 0, then that becomes the Fourier transform of that. You know that if sigma equals 0, that's just the Fourier transform of xt. Okay. So what about in the discrete time Fourier transform? In the discrete time Fourier transform, the sample sequence is multiplied e to the minus j omega n. So n is a sequence index like that. So what's the meaning of e to the j omega? At here, e to the j omega is a unit circle. Okay. So, okay. E to the j omega unit circle, like this one. So e to the j omega, we express that one into x e to the j omega in the DTFT. But in the continuous domain, we are using the x j omega. So that's this axis. So at this moment, the omega is a normalized one. So we can taking minus pi to the pi is the maximum value, the range of this value. So we starting from minus pi to the back to the here. If omega equals 0, if this is 0, then that's the DC terms. So this is 1 actually. If omega equals 0, then it should be 1, and this point is minus 1. Okay, and omega changing from 0 to the pi, that this becomes the pi. So what about in the corresponding in continuous domain? It's a likest frequency, that is a sampling frequency, half of the sampling frequency, minus j omega s over 2. So that's the pi point, minus pi point. And j omega s of 2, that's the another Nyquist frequency for the positive side. That's the pi. So minus pi to the pi is minus Nyquist frequency to the positive Nyquist frequency. This range is the unit circle of that one. So that's why we expressed in the DTFT, it's the circle. Okay, this one shows that the unit circle. So unit circle changing minus pi to the pi, but this one changing minus Nyquist frequency to the positive Nyquist frequency. But in sometimes we are using the omega as a 0 to the 2 pi. So that is also used. Then omega equals 0 is this point. Okay, 2 pi. Sorry. So if omega is increasing, then it follows this unit circle and passing minus 1. That's the Nyquist frequency, and increasing to the 2 pi. So 0 to 2 pi index is this one, 0 to 2 pi. Okay, we prefer this minus pi to pi, pi to pi, but sometimes we are using the 0 to the 2 pi, but it's the same. It's because it's a periodic. You know, the circle is periodic like that. But in the continuous domain, 0 is this one. Omega equals 0 is corresponding this point, and 2 pi corresponding to j omega s. So you can refer these sections. So this point is this point, and this point is this one. So the one circle from 0 to 2 pi corresponding to 0 to the j omega s. This point corresponding to 2 pi. This one is this DC. So 0 and 2 pi, in fact, the same positions at here. That's the 1. Okay, so you need to understand that the difference between the continuous Fourier transform and DTFT. In a DTFT, we are using the normalized frequency. Usually we are taking minus pi to the pi. Then we can using the minus omega s of 2 and plus omega s of 2. This range is this unit circle. Okay, so that's the DTFT, and the relationship between the Fourier transform. The Fourier transform is a continuous one. Continuous Fourier transform and DTFT are related in this way. So, and what about G transform? In the G transform, compared to Laplace transform, when we consider the Fourier transform, to make it converge, we apply this term, we added these terms, the exponential terms. So if we choosing proper sigma, then we can make it converging. So that is the topic of region of convergence. That is related to region of convergence. That is always the limiting the sigma value for the converging property. So it's quite similar for the G transform. In case of G transform, you can see here that the Laplace transform, the DTFT cases e to the j omega terms are this one. And here we added this one, not just only j omega. We are using the minus n in the DTFT, but in the G transform, look at here, we introduced R here. In case of Laplace transform, we introduced sigma. So sigma is added in the Laplace transform, but in the G transform, we added R. So to make it converging. So you can see here, this one is just a power series. Okay, summation of the power series that will give the G transform, and we make the G with R times e to the j omega. So this is the definition for the G. Okay, and you can see here that xn times R times e to the j omega to the minus n, that is G transform. We need to specify region of convergence of that one. That is always expressed by the radius of the circle. You know that R to the e to the j omega is actually circle with the radius is R. So radius is R, and this one means that kind of circle. So in the G transform, region of convergence always expressed by these circles, and the radius will be given as a region of convergence. In the Laplace domain, it is always expressed by sigma. Sometimes it's bigger than some value or less than that one, like that. But it's the same. Radius is bigger or smaller. That is the region of convergence in the G transform. And look at here that if we re-express this one into this way, this one is R to the minus n is this part, and if we applying the minus n power to the j omega, that becomes this one. Then this one just the DTFT of this sequence. Okay, so the G transform is actually Fourier transform of these terms. It's quite similar for the Laplace transform case. So if you comparing, you can better understand it by use of this similarity. Okay. If we are taking R equals to 1, then it's just the DTFT. Okay. And also we are usually taking unilateral G transform. That means it's the right-sided signal. Signal only exists and n is positive case. Okay, that is a unilateral. It's a right-sided signal actually. So G transform can be summation from 0 to the infinity, not from the minus infinity to the infinity index. So this is the unilateral G transform. So you need to understand what's the meaning of unilateral G transform. That's the right-sided signal, or sometimes left-sided signal. what's the relationship between the G transform and Laplace transform? The concept is quite similar. To make it converge, we introduce the sigma, but in the G transform, we introduce the R to make it converge. Okay, in a continuous domain, this one is a continuous signal. We are taking the sample by applying the sampling signal. This is the sampled signal. Okay, that can be expressed by this delta impulse train. And if we're taking the Laplace transform of this XS, that's the XSS. So we take the Laplace transform of the sampled version. Then this one is XS. Okay, from here to here is the XS. And this is e to the minus SD. This is definition of Laplace transform over X sampled signal. So this one just express the Laplace transform of sampled signal. Then, by definition of the delta function, t is non-zero only t equals to kts. So we can replace the old t with the kts. Then XSS Laplace transform of a sampled signal are given like this way. From here, you may know that you may know these terms. So at here, e to the s times t times s is defined as a g. Okay, ts is a sample period. We make a sampling, so sample period is ts. At here, if we taking the g as e to the sts, so ts is normalizing factor. As we have done in the DTFT, you know that omega times ts is the omega, normalized frequency. Okay, this is the normalized frequency. It's quite similar. So we are taking the s times ts is normalized by the sampling frequency. Okay, by taking this ratio, we define the g terms. Then we can express that one in this way. You can compare this derive and this one. So we use these terms r times e to the j omega was g. But we know that the s can be expressed by real term sigma plus j omega. Okay, then you may understand the relationship between r and omega. E to the sigma times ts and e to the j omega times ts. Okay, so this term is r. Sigma times ts is r. Okay, and e to the j omega equals to e to the j omega times ts. It's obvious this is normalized frequency, and the sigma is normalized, that becomes r terms. Okay, so we can express the g transform in this way. This is x to the g. Now compare the relationship between the Laplace transform and G transform. You know that this one is actually Laplace transform for the sampled signal, and we just replace the change of variable of this one by this variable. G, let the g is e to the sts. So normalize the factor of the e to the s. Then it just becomes the G transform. Just a change of variable. By this change of variable, the S domain becomes the G domain. Okay, what's the relationship then? This point corresponding to this point, and this point, this Nyquist point, these 2 points are corresponding here. What about the left hand side? any this point, if you see here, that is will mapping inside of this circle. So left hand side of the S domain should be inside of this circle. Outside of here, that's the right hand side. This part will be outside of this part. So carefully compare S domain to the G domain. So what's the difference? Okay. So regional convergence has the same definitions. S has a regional convergence that will confine the requirement for the sigma. Then that will automatically becomes the requirement for the regional convergence for the G transform. The next topic, let's consider the inverse G transform. We talk about the G transform. Let's summarize that one. If we have X n sequence, okay, then the G transform of that Xn is Xg are given okay, I think I should take equation X of n. I would like to take a G transform okay, I think this symbol is better. By taking the G transform, X over G are defined by n changing from minus infinity to infinity, and X of n G to the minus n. This is G transform. Okay, but G transform can be understood by these equations. It means G transform can be understood by replacing G with R e to the j omega, then R to the minus n, and C dot e to the minus j omega n. So this one, G transform, is actually Fourier transform DTFT of this DTFT of these terms. Okay, this is the G transform. Then what is the inverse G transform? To find out that one, let's take in the, inverse DTFT. Okay, inverse DTFT of this one. Okay, we take the DTFT of this this sequence. So we can take in the inverse DTFT for this circuit, for this system signals. So we can using 1/2 pi and minus pi to the pi, and the okay, let this one as x r e to the j omega. You know that this one means the g. Okay, we define the g as since g is equals to r, this is g. Okay, this is g. So g is replaced by this way. So we can write this one. In case of DTFT, the radius is 1, but at this moment the radius is r. Okay, that's circle. So we are taking the integration over this circle, and e to the j omega t n, sorry, n d omega. This is definition for the inverse DTFT. So if we're taking the inverse DTFT with respect to xg, that will become this one. So we can express xn with by multiplying r to the n. So xn can be expressed by 1 over 2 pi taking integration over 2 pi range, and x over r e to the j omega, and here we multiplied r to the n to the right hand side, then it becomes r, okay, r e to the j omega over n and d omega. Okay, this one is the inverse DTFT. But from here we define the z equals to r e to the j omega. Then dz will be at this moment the variable is omega changing from minus pi to the pi over the 2 pi area. So by taking derivative dz, r is a constant at this moment. The circle radius is the same. The integration domain, you can hear that the integration domain is just a circle. Okay, this one is a circle, radius is r. So this is r e to the j zeta, j omega. Okay, that's this one. We are taking the integration over this circle from angle minus pi to the all the way down here pi, minus pi to pi. That's the 2 pi range. So we are taking integration over the circle. So r is constant. So the dg is only function of omega. So that's why r okay, j omega r e to the j omega d omega. So d omega are given like this way. So we can rewrite this one into this way, 1 over 2 pi, and you need to know that the d omega are equals to j omega r e to the j omega over dz. Okay, d omega should be, this d omega should be replaced by this one. Okay, so we can express that one. Omega is, j is expressed on here, and we integrate on a contour, this circle on this contour, and x over r e to the j omega is g. Okay, and this is g to the n, but this is another g is divided here. So at this moment g to the n minus 1, and c dot dg. So we replace the d omega with this value, then we have the inverse inverse Z transform expression over here. Okay, this is the inverse Z transform of the sequence. So we derived the how to find out the inverse Z transform. Okay, but this one is the complex integrations. dz is the same as a Laplace transform, is a complex number. So the complex integration can be done by use of residue theory. Okay, iteration contour is always taking the counterclockwise, minus pi to the pi in this directions, or 0 to the 2 pi. In any way, we can using the 0 to the 2 pi or minus pi to the pi. Anyway, we need to take the counterclockwise contour directions. That's this requirement. And the center is origin, and the radius is out. That's the integration contour. Okay, we can take the contour integration by use of residue theory, as we have done in the Laplace transform, which is the same. And what is the reason of convergence of xg? If xn is finite duration cases, then region of convergence is a whole G plane. Okay, and if xn is a right-sided signal, then region of convergence is all G outside of the unit, outside of the circle centered at origin. It means that in the Laplace transform, S domain is this one, and in the G domain, the radius is this R, and this point is expressed by R times e to the j omega. Okay, this one is G domain, this one is S domain, this one is DC, and this is maximum frequency. In the Laplace transform, the right-sided signal, the region of convergence are expressed by the certain pole, the pole to the right-sided. Then this becomes the right-sided signal. Okay. Then adhere that in the same way, the outside of this point is outside of this circle. So this is the right-sided signal. Okay, that's this part. So xn is a right-sided signal, then region of convergence xg is outside of the circle. Okay, certain radius of R. So region of convergence are given like that. Okay, this kind of okay, here is R. So that's this one. Then this is right-sided signal. Okay. If xn is a left-sided signal, in case of Laplace transform, it was left-sided. This is the region of convergence. Then it is a left-sided one. Left-sided case is inside of the circle. Then, in this case, it's a left-sided signal. If xn is a two-sided one, then in the Laplace domain, it was certain zones existed. So, in the Laplace transform, if the region of convergence in the certain zones, right side and left side of these poles, then in the G transform, it is certain donuts. Like this one is R1 radius, and this one is R2 radius. Then this one can be expressed in between these circles. So in the Laplace transform, it's a straight line parallel to the j omega axis. This is j omega axis. So parallel to the j omega axis. But in the G transform, all the parallel line is expressed by the circle. Because of this expression, you know that j omega is expressed by e to the j omega. Okay, this is circle. This one is a straight line. Okay. So we talk about that the region of convergence of the xg is a finite sequence, then the whole G plane is a region of convergence. If xn is a right-sided one, then region of convergence expressed by in this way, the outside of the circle. But if xn is a left-sided one, then it's inside of the circle, is the region of convergence. And if it's a two-sided one, then there's a certain zones that exist like that. Here shows some example. The first one is a finite duration sequence. xn sequence has non-zero values, only n is 0, 1, 2. At that case, n is 0, 1, 0, x0 is 1 and 1. x1 is minus 2. And x3, x2 is a 3. Okay, like that. It is a finite duration. Okay, then take the G transform. Then n equals, even though we're taking the summation, the whole range, but n has only non-zero value at the n0, 1, 2 cases. N equals 0 cases, x0 is 1, and if you're taking n equals 0, then is 1. So that's this one, n equals 0 cases. N is 1 cases, the x1 is -2, and we have g to the -1 at this case. And here x2 is 3, and g equal 2. So that's this one. So xg expressed in this way. In this case, it's a finite duration, so the region of convergence is whole range of that one. What about the right-sided example? Here is a unit step. Okay, unit step sequence is this one. By taking the G transform, it's this one. So the unilateral indexing, so it's n equals 0 to the infinity, so it's g to the -n. You know that this one is a summation of power series. So 1 minus g to the minus inverse over 1. This is the G transform of a unit step sequence. And to be converging, you know that this should be less than 1. In the power series, the ratio should be less than 1. So this is that conditions. Then G is outside of this unit circle. So this is the region of convergence for this G transform. What about the unilateral exponential sequence? So here is a exponential sequence, and then we can take the G transform by this summation. It means that the x over G is a summation from, you know that because of the unit step, n should starting from the 0 to the infinity. It's a right-sided signals, and a n times g to the minus n. So this one can be understand in this way: 1 minus ag to the minus 1 over 1. So at here that you can see that the a times g, a over g to the n. So this one is the ratio factor. So this ratio should be less than 1 to converging. So this one means that this region of convergence, and G transform will be in this way: G minus A. Okay, this is G transform, and the region of convergence defined in this way. So right side is sequence has always seems like this one, certain larger than outside of the circle. Okay. What about the left-sided one? Left-sided one is a left-sided unit step. Then we need to taking summation minus infinity to 0, and then we can change a variable with a minus n. Then it will give in this way. So this is it. In these cases, to converging, the absolute value of g should be less than 1. So this is the region of convergence of the left-sided unit step. Okay. Lastly, consider two-sided case. Two-sided case are shown here that if n is a positive, and it's positive, it's alpha to the n, and it's negative, beta to the n. So we would like to take the G transform of that one. Then we need to summation of this one. So we can decompose the positive sequence and negative sequence in this way. So in the positive sequence, it's alpha to the n and g to the minus n. And the summation minus infinity to minus 1. Okay, minus 1. And the beta to the n and g to the minus n. And then we can add 0 over here and subtracting minus 1. You know that n equals 0, that is 1. So we can add 1 and subtracting 1. And taking summation from 0 to the infinity, it's the same the previous one. And we change a variable, we replace the minus n to the n. Then it becomes like this way. So we replaced at here minus n with n. Okay, then it becomes in this way, and the minus infinity becomes the infinity, and 0 becomes the 0. And then by the summation of a power series, it's given like this way. To be converging, this part should be less than 1 and this also should be less than 1. That's why the region of convergence looks like donut shapes. So we talk about the Z transform for each case is finite duration, and the right-sided case, and the left-sided case, and the two-sided case. We talk about that one. Here shows an example how to take in the inverse Z transform. We talk about the residue theory. Here is a two poles. One is a minus, one is a 0.5, and the other one is a -2. Okay, here is two poles exist here. So we need to find out the residue to taking the inverse Laplace transform. First, consider right-sided case. In the right-sided case, is the maximum radius. At this moment, the radius is 0.5 and 2. Okay, absolute value is 2 radius. To become right-sided, the maximum radius outside. Okay, so we have two circles. So one is 2, the other one is 0.5. So to become right-sided, the region of convergence should be outside of here. Okay, so that's this part. In this region of convergence, we can find out the residue of this one. The residue can be found at the first G approach to the 0.5, and we multiplied this residue value at here and taking the G transform, inverse G transform at here, inverse G transform as a G to the n-1. We can refer to the inverse G transform definition over here, that we need to take a complex integration of these terms. The reason why n is reduced 1, that's this part. You know that this is G. G is divided from here. Okay, by converting the omega to the dg, the n is reduced to 1. Okay, okay, we need to take a residue value of this one. Then you can find out the residue. Then this is the sequence for the 0.5 residue, and another pole is -2. So G approach to the -2, and we need to calculate this one. That will give this result, and then we can find out the original sequence like that. It's a right-sided sequence. That's why the UN is added here. And what about the left-sided one? In case of left-sided one, the minimum radius, this is 0.5 radius, inside of the this circle becomes the left-sided one. This is the region of convergence for that. Okay, then it becomes left-sided. In case of left-sided, it's a negative, and this is negative part are given like that. This one is a left-sided one. And what about the two-sided cases? Two-sided cases in between these two circles. So this is the regional convergence. Then that becomes the two-sided cases. Then outside of the 0.5, so this one is a right-sided one, but this part becomes the left-sided one. Okay, then this is right-sided interpretations, and this one is a left-sided residue analysis. This is how we gonna taking the inverse G transform. Lastly, I'd like to compare the Laplace transform and G transform. It's quite similar. Laplace transform are used for the continuous system. Continuous system described by these differential equations. Left side is output differentiation, a to the sum of differentiation of the output. Right hand side is input differentiation weighted to sum. So by taking the Laplace transform, each time derivative converted into S polynomial, and the transfer function are given like that. And in the G transform, applied to the discrete system expressed by the difference equations, and the difference equation can be converted by G transform, and then it gives a transfer function such as like this one. It's quite similar, but one is this kind of S domain. It's a rectangle, Cartesian coordinate. But in the G transform, it's a conformal mapped. It's a circular one. So from -pi to the pi, that's the Nyquist rate zones. Okay, the left side is corresponding the inside of this circle, and the right hand side is outside of this circle. This is unit circle like that. So it's a this is the similarity between the Laplace transform and the Z transform.